We all know what rain feels like, right? But what about measuring it? Everywhere on the planet at the exact same time. Yeah, that's a whole other level of challenge. Today, we're going to look at exactly how NASA and its partners pulled that off by building, get this, a global rain gauge in space. I mean, think about it. You can put a rain gauge in your backyard, no problem. But what about, I don't know, the middle of the Pacific Ocean? That's a huge, gigantic blind spot on our weather map. And it's not just the oceans. How about the top of the Himalayas? Good luck sticking a gauge up there. And look, these aren't just fun trivia questions. Knowing this stuff is absolutely fundamental to understanding how water moves around our planet. You know, the water cycle. So for pretty much all of human history, the answer was, well, a guess. An educated guess, maybe, but still a guess. We were completely missing the big picture. That is, until we finally got a new set of eyes up in the sky. All right, so let's talk about these blind spots. I mean, our planet is more than 70% ocean. Now you throw in all the remote mountains, the massive deserts, and you start to realize, wow, for most of the Earth, we were basically flying blind when it came to rain and snow. These places were total data deserts. So what's the solution? It's a mission called the Global Precipitation Measurement, or GPM for short. And this isn't just one satellite doing all the work. No, it's a whole team, an international constellation of spacecraft, all working together. The best way to think about it is like an orchestra in orbit, with all the different instruments following the lead of one single, very important conductor. Okay, so an orchestra of satellites, how in the world does that actually work? Well, it really all hinges on that one conductor satellite, which acts as the gold standard for everybody else. And here it is, the GPM Core Observatory. This thing launched back in 2014, and what's really cool is its orbit. It's at this unique 65-degree angle, which means it flies over most of the planet. And, this is key, it sees weather at all different times of day and night. It's not just seeing the same spot at, say, 2 p.m. every day. But the real superstar, the main event, is the instrument it has on board. So this GPM Core satellite is carrying the most advanced weather radar ever put into space. Seriously, it lets scientists do something incredible. They can actually peer inside a storm cloud and measure the rain and snow that's in there. And this really shows you what a huge leap forward we're talking about. The old mission, called TRMM, it had a radar with just one frequency. GPM has two, and trust me, that is an absolute game changer. It's like going from a black and white sketch of a storm to a super high-res 3D color photo. So why are two frequencies such a big deal? Well, here's a good way to think about it. Imagine one frequency can see the big, heavy, chunky raindrops. The second frequency, though, is way more sensitive, so it can pick up on the small, light stuff, like drizzle and snow. It's kind of like looking at a big crowd of people. If you can only see their hats, you're missing half the story. But if you can see their hats and their shoes, suddenly you get a much, much better picture of the whole person. And this chart breaks it down perfectly. You can see the Ku band, that's great for heavy and moderate rain. But check out the Ka band. It's so much more sensitive, it can detect that really light rain and even snow. We're talking about precipitation that older satellites would have just completely missed. And that's absolutely crucial if you want to get an accurate number for the total amount of water coming out of the sky. Okay, so we've got all this incredible data pouring in from this orchestra of satellites. The big question is, how do you turn all of that into a single, seamless, global map of rain and snow? Well, it happens through a really clever process called IMERG, and you can think of it like a 4-step recipe. Step 1, all the different partner satellites gather up their data. Step 2, the GPM Core satellite, our conductor, calibrates everyone to make sure they're all on the same page, speaking the same language. Step 3, a super smart algorithm fills in the gaps between satellite passes by tracking the motion of the storms. And then finally, step 4, the whole map gets a reality check against actual rain gauges on the ground, just to correct for any little errors. And what's really fascinating here is that the final product isn't just one thing. It actually comes in 3 different flavors, depending on who needs it and how fast they need it. You've got the early version, which comes out in about 4 hours, perfect for, say, a hurricane tracker who needs data right now. Then there's the late version, a bit more accurate, great for your daily weather forecast. And then you have the final run. This one takes about 3.5 months to cook, but it's the absolute gold standard for climate researchers. So you can see there's this constant trade-off between speed and accuracy. All right, so the whole system sounds incredible on paper, but how does it actually stack up in the real world? Let's take a look at its report card.
Okay, check this out. On a monthly scale, and that's what's really important for climate science, the system is just ridiculously accurate. It has a correlation of 0.94 with ground gauges. To put that in perspective, that's like getting a 94 on your final exam. It's a straight A student. It means the satellite data and the ground data are almost a perfect match over the long run.
But, no one's perfect. And GPM has its challenges too. In really complex mountain regions, it can underestimate rain by a whole lot, sometimes 30 to 50%. Measuring snowfall accurately is still a huge challenge. And because a satellite can't be everywhere at once, it can sometimes miss those really quick, fast-moving storms. Oh, and yeah, it has a big blind spot right over the North and South Poles.
But here's the thing about science. Knowing your limitations is what pushes you forward, is what drives innovation. And you better believe scientists and engineers are already hard at work designing the next generation of instruments to plug every single one of these gaps.
So what does the future look like? We'll get ready for this. How about adding a third radar frequency, one that's perfectly tuned to measure snow, which is one of the biggest weak spots right now? They're also looking at using deep learning and AI to make the data even sharper and the forecasts even faster. And then there's the holy grail. What if you could merge the space data perfectly with all the ground radars we have? Or even crazier, put a sensor in a geostationary orbit so it just stares at one spot, watching storms evolve in real time, minute by minute. That means no more gaps. Ever.
And that really brings us to why all of this matters so much. This quote just nails it. As our climate changes and we see more and more extreme weather, both rain and snow, having this kind of continuous, accurate, global record, it isn't just a nice to have for scientists. It is absolutely essential. It's about protecting lives, protecting communities. Look, the GPM mission was truly revolutionary. It gave us a whole new way to see our planet's lifeblood, water, as it moves around the globe. It literally filled in the blank spots on our map. But as this technology keeps getting better and better, it leaves us with one massive question to think about. As our planet's water cycle gets more and more intense, what will the next generation of these instruments reveal?